before we get into any kind of formulas for this, I want to show how we can use tables like this to just not have to deal with any formulas. And I would much rather, even as a math person, I would much rather just kind of think my way through something than to ever try to bust out any formulas. So let's actually talk about that. And the very first thing we need to talk about is why I'm calling this thing a contingency table, because this only works if it's a contingency table. All right, so we've got this general social survey that they did in 2016 that asked whether people believed in life after death, right? So belief in afterlife. So I've got yes or no. And we've got that split across gender, whether they're male or female, okay? So the thing that's essentially making this a contingency table instead of just a regular kind of like two-way table that we maybe often see with these two different variables of gender and belief in afterlife is that my rows are mutually exclusive. Somebody would only select male or female, and same thing with belief in afterlife, right? Somebody would only select yes or no or undecided, right? So they can't select both, right? And that's the thing, right? Gender politics aside, that's not what I'm trying to talk about here. They would only be allowed to select one of these. And if they selected more than one, maybe they're just removed from the sample, whatever, it doesn't matter. The point is, as long as no one appears in more than one cell, that's what we're trying to avoid here. It has nothing to do with anything about judgments, about, whether someone can be undecided but kind of lean yes or something. It's that they can't get counted twice, right? So when I add up these numbers, 1,230, 859, 357, and 413, it needs to add up to the total sample size. It needs to add up to how many people were actually surveyed here. Because if I've got somebody listed twice here, right, if they said they're male and female or whatever, or neither, right, neither would not appear anywhere, right, so now I'm missing somebody. If they selected both, now they're double counted, right, their answers count double of other people's answers. So again, this comes up all the time in these kind of surveys, especially like with ethnicity, where people have parents that are from different ethnicities. Now what do you mark, right? Like it just becomes a thing where, okay, just pick one and like whatever, just to make sure that these probabilities or these percentages, as we're going to calculate them, just come out to correct numbers and nobody's being undercounted or double counted in it. Okay, so that's what makes this a contingency table, so that I can work with it to find any kind of typical probabilities that we'd want to find. So let's go through some examples of that. But before I do that, I want to just show you right behind me. I've just kind of copied over that table that I made there. The very first thing I ever want to do when I get these is just find my totals, right? So I'm going to find my row totals, and I'm going to find my column totals, and then my actual like grand total, because I'm going to need all those numbers as I go through this anyway. And this is just making sure that I don't make any calculation errors in it. So 1,230 plus 357, that's 1,587. Before I move on though, what is that? Okay, that's the number of people total that marked that they were male. Okay, that's what that is. All right, so let me put that here, total. Okay, so this 1,230 plus this 859 gets me 2,089 people marked yes, they believe in life after death, right? And this 770 that I get here is going to be the total number of people that said either they don't believe in afterlife or they're undecided, right? They're not firm believers in an afterlife. Okay, so we got 770 there. And then finally, this 859 plus 413, let's see, 1,272 said they were female. Okay, so now these two numbers actually represent the whole table, right? This is both of these two cells, and this number is both of these two put together. So if I want to find the grand total, in other words, how many total people were in this survey, I either add these two together or these two together. I don't want to add all four because now I'm double counting how many are in the table. Okay, so I'm going to just add these two together just because it's easier to do by hand. And I get 2,859. A good way to double check that you didn't make any mistakes, though, is to go ahead and add these two together also. These two should also add up to the same number, right? Because this is these two cells, and this 770 is these two cells. So these two are also counting all that same stuff. This better add up to the same thing, and mentally doing the arithmetic here, it does, right? So now I've got my column totals, my row totals, and my grand total. Now I've got every number I need to answer any probability that we're asked. So let's answer some. Okay, what's the probability that someone believes in an afterlife? Okay, probably that someone believes in an afterlife. Well, that would just be, okay, so probability of saying yes here, right? Based off of how this survey was set up, that was the probability that someone says yes at all. This is here, right? That's how many people said yes. 2,089 out of the total number of people in the sample, or in this survey. 2,859 people. Okay. So that's that. I didn't think too hard about that, but just know that when we're asked for probabilities of just one thing happening, that's either a column total or a row total. It's not found inside the table, it's found in the margins, which is why it's actually called a marginal probability. But that's a vocab word, is not important for us. Just know that that would be either a row total or a column total, right? This 2,089 is a column total. Okay, let's look at another one. What's the probability that a randomly selected person is a female that believes in an afterlife? Okay, so in real life, you could always just ask somebody to clarify for you. But here, on your homework or something like that, you won't necessarily have that advantage. You could always send me a message, but just know that I'm going to kind of stick with this kind of wording where what's the probability that a randomly selected person? In other words, we're not assuming anything about this person. This is just a randomly selected person. And so in other words, if you're thinking, oh, we're doing this conditional probability stuff, and so maybe we should be assuming they're female, and then what's probably they believe in an afterlife? No, I'm going to use totally different phrasing for that. This is just a randomly picked person. Now I'm looking for, okay, if they're randomly picked, what's the probability that they're female and believe in an afterlife? Okay, so now we're looking for the probability that they're female and they say yes, they believe in an afterlife. Okay, so we know we can do some like multiplication and stuff to figure this out, but it's much easier than that with a table. We're looking for the probability they're female and believe in an afterlife. Isn't that what this is, right? So a female and said yes, they believe in an afterlife. And that's these 859 people, right? Those are the only people that are both female and believe in an afterlife, okay? So that's 859 people, and we're randomly selecting this person. So it's out of just any of these 2,859 people. That's it. Okay? So when it's an individual event, get that from the margin totals. If it's a compound event, two things happening at the same time, right? And, specifically and when we're not assuming anything, there's no conditions on it, it's just a randomly selected person, that number just comes straight out of the table, out of how many people we have total. Now let's switch that just a little bit as we do a couple of different questions. All right, given that someone is a woman, well, now that sounds like I'm not just randomly selecting somebody. This is specifically from the people that marked female here. What's the probability she believes in an afterlife? Okay, so given that someone is a woman, right? So I don't know why I'm writing a G there. So we're looking for the probability, and remember, given that should be a key word that makes us think of conditional probability. The two common phrases that you'll see for conditional probability are given that and if, right? So this will be given that, and remember we actually read this bar that we put in conditional probability out loud as given that. So if we say, given that they're a woman, we're given that they would be marked as female in our table here. Okay, given that information, what's the probability they believe in an afterlife? Okay, so this is different than the situation we had right here where we were just randomly selecting anybody. Now we're told this is not a male, right? So we can just ignore this whole top row. That's irrelevant for us. And where that really comes into play is that we're only looking at these 1,272 females. We are not looking at the total 2,859. Okay, so we just want this 1,272. For the bottom, remember the bottom of my fraction is always going to be the total number of possibilities, okay? So there were 1,272 total females, okay? And now, of those females, again, I don't want to pay attention to any of this, of those females, how many of them believed in an afterlife? Well, that's just these 859. So, if we look here at our answers between here and here, we see the logical difference, which is that this one was talking about anybody, and this was talking about specifically only women. And we also see the mathematical difference that actually the top ends up being the same because in the end, it's both women that believe in an afterlife. Okay, so that kind of makes sense. But out of what group, right? Here it was everybody. And over here, it was only looking at women. So we can also think of conditional probability as a subgroup, that we're just looking at a subgroup of this total population, right? Okay, let me just do one more. I know this video is already getting a little long, but I just want to finish this up. All right, if someone believes in an afterlife, what's the probability that they're a woman? Okay, well, this is pretty close to what we just did, but with things reversed. Right? So if someone believes in an afterlife, and again, if and given that should be immediate verbal cues that we should be thinking about conditional probability. And the condition here is if someone believes in the afterlife. Okay, well, that goes over here. Right? This thing that we're assuming is true goes over here. What's the probability that they're female? Okay. So let's find this. All right. So just as I had thought about this before, I want to think about the condition first, because that'll set the bottom of my fraction. I only want to look at the people then that said yes, right? If someone believed in an afterlife, well, that means these people are irrelevant. I'm only looking at the people that believe in an afterlife, right? When I say if someone believes in an afterlife, that means I'm assuming that's got to be true. I only want to look at those people. Where there's 2,089 of those. All right, and of those 2,089, right, of these people, how many were female? Well, that's this 859 again. So we see that we're kind of getting the same number in the top. The difference for all of those three questions is what group am I looking at? If we're just looking at any randomly selected individual, I use the total for all of the cells in the table, right, 2,859. If I'm looking at the subgroup of just women, I want to only include that total number of women as the bottom of my fraction. And now that I've changed it to be, I'm not assuming they're a woman, I'm assuming they believe in an afterlife. Well, now I've only got however many believed in an afterlife for the bottom. So these two, the difference is which subgroup we're actually looking at. So notice these two numbers are not the same, okay? So this kind of gets us to a general thing that you should just know, which is that the, sorry, I'll come back to that. In general, if I switch the order of what we're finding the probability for and what's the condition, if I swap the A and B here, I generally speaking, will not be getting the same answer. I can come up with some convoluted example where they're the same, but in general, they are not the same. And so you've got to work with what you're actually given in that problem.